Welcome back to the Building Code Pros podcast, your expert resource for navigating the world of building codes. In today's episode, we're taking a closer look at a crucial topic. Let's get started. Our focus today is a deep dive into the absolute foundation of residential structure, the general requirements for wall construction, primarily codified in the 2024 International Residential Code, Chapter 6. This isn't about bracing or shear walls yet. This is really about ensuring the vertical and horizontal integrity of the basic structural skeleton.
Exactly. When we talk about walls, we're talking about the entire load path. R601.2 lays it out pretty clearly. It establishes the non-negotiable mission. Wall construction must handle every imposed load, gravity, wind, snow, you name it, and transmit those resulting forces cleanly to the structure below. Doesn't matter if you build with wood sticks, concrete, or SIPs. If that load path fails, well, the building fails.
Right. Let's start with the standard then, the reference point for nearly all builders. Wood framing under R602. Instead of just reciting every grade stamp, what's the core principle the code is trying to enforce regarding, say, material quality and how that pleat system functions?
It really boils down to reliability and continuity. For quality, that's R602.1, It's simple. Sawn lumber has to carry an accredited grade mark, period. You need that guarantee of structural performance.
Makes sense.
Now look at the studs. R602.2 minimum, number 3 standard or stud grade for anything supporting real weight. There's an exception for utility grade, but it's narrow.
Yeah.
Non-bearing partitions or maybe bearing studs, not supporting floors, and even then you have to follow specific spacing tables. The real insight here is that every vertical member must be strong enough, to carry its share from the sole plate right up to the top plate. Continuity.
Okay, and the top plate, R602.3.2, that's the critical structural bridge, right? Why is the double plate mandatory in prescriptive framing? What's it doing?
Well, the double top plate is basically the code's simple way of creating redundancy and, frankly, dealing with inevitable field issues. It's a minimum 2-inch nominal thickness, runs the full width of the studs, and the key requirement is that 24-inch offset on the end joints.
Ah, the offset.
Yeah, that overlap lets the top plates act together, kind of like a mini beam. It bridges minor gaps and helps distribute concentrated loads coming down from rafters or trusses. It ensures the load hits multiple studs below instead of just one.
I see framers sometimes trying to save time, by using a single top plate. What kind of complex hoops do they have to jump through to meet that exception? Sounds like trouble.
Oh, it is. I mean, you can use a single top plate, but you immediately swap simplicity for some highly precise engineering requirements. To compensate for that missing top plate, you absolutely must use galvanized metal ties at corners, intersections, all splices. And get this, for a straight wall butt joint, the code specifies a 3-inch by 12-inch, 0.036-inch thick galvanized steel plate, and it needs 12 8-day box nails on each side of the joint.
12. Wow.
Yeah. It's an explicit steel reinforcement just to replace the wood's inherent strength and that offset capability you lose.
That really drives home the point that the default method, the double plate, is often the simplest path to compliance. Staying on this topic of alignment, R602.3.3, this seems like where the reality of framing layout bumps up against the structural necessity of the load path.
Correct. The code assumes a straight, continuous load path. That's the ideal. So if your joists or trusses or rafters are spaced more than 16 inches on center, you've got to align the bearing studs beneath them. They have to land within 5 inches of the supported member.
5 inches, okay.
If you miss that 5-inch window, you've basically compromised the path. The load isn't transferring directly down. But the code does give you 3 ways to fix that misalignment without tearing everything out, which is good.
Okay, what are they?
You basically stiffen the bridging element, the top plate system. You can either use 2-inch by 6-inch top plates instead of 2x4s, or you can install a third top plate, or you can install solid blocking, the same size as the studs, directly beneath the unsupported portion of the double top plate. All 3 solutions essentially beef up that horizontal element so it can properly span the distance over to the load-bearing stud.
Got it. So you're reinforcing the bridge.
Exactly.
Okay, let's shift gears. Here's where the fight often starts on a job site. R602.6, running plumbing, wiring, HVAC, cutting through structural wood. Builders really need to know that these notching and boring limits aren't arbitrary, right? They exist to preserve the structural core of the stud.
That's absolutely the key insight. For exterior walls or any load-bearing walls, you are heavily restricted. Notching depth cannot exceed 25% of the stud depth. That's just 1/4. Boring is slightly more forgiving, maybe, but still capped. The hole diameter cannot exceed 60% of the stud depth. And crucially, the edge of that hole must maintain at least 5/8 inch of solid wood to the stud edge.
5/8, okay.
The moment you cut or bore, You are reducing the load-carrying capacity of that member. Simple physics.
And what if you need a truly large hole in a bearing wall, say for a bigger pipe?
Okay, if a bored hole exceeds 40% of the stud depth in a bearing or exterior wall, that stud must be doubled. You have to sister another stud right next to it to compensate for the loss of material, and you can only run a maximum of 2 successive doubled studs with holes that large. This contrasts pretty sharply with non-bearing partitions. There, the notching limit jumps all the way up to 40% of a single stud depth. So the rules really depend on the wall's function. Is it carrying load or just dividing space?
That's a critical distinction. Now let's talk about what feels like the absolute structural danger zone. Cutting the top plate, R602.6.1, you're literally cutting the primary tension member that ties the whole wall together laterally. What happens if, say, an HVAC duct requires cutting more than half the width of that plate?
Yeah, that's a big one. When you cut that top plate by more than 50% for piping or ductwork in an exterior or load-bearing wall, you must immediately restore the Tenthal continuity. It's not optional. The code requires a mandatory remediation using a specific galvanized metal tie, minimum 0.054-inch thick, 1 1/2 inches wide, and it has to be fastened across the plate at each side of the opening. It requires not less than 8 10D nails on each side, penetrating at least 1 1/2 inches into the wood, and the strap itself needs to extend 6 inches past the opening on both sides.
That's specific. 8-10 nails each side.
It is. It's a classic example of replacing lost wood strength, specifically the tension capability, with engineered steel.
Excellent point. Okay, we focus mostly on vertical members and plates. Shifting briefly to horizontal spans, what does the code say about openings in non-bearing walls? I feel like these often get framed overly conservatively.
They often do. R602.7.4 offers a really sensible shortcut for non-bearing walls. Load-bearing headers, like big double 2x10s or LVLs, they're simply not required. So a single flat 2-inch by 4-inch member is perfectly fine as a header for openings up to 8 feet wide.
8 feet, just a flat 2x4.
Yep, if the vertical distance, the space between that flat 2x4 header and the parallel nailing surface above, like the bottom of the top plate, is 24 inches or less. And critically, in this specific non-bearing scenario, you don't even need cripple studs or blocking above that header. It simplifies the framing immensely, saves time and material.
Good tip.
And before we transition to alternative materials, let me highlight one potential load path killer that starts way down at the foundation, or slab. It's R601.2.1, the compressible material rule. I've seen inspectors fail entire divisions because of this seemingly small detail.
Really? What is it?
Okay, any compressible floor covering, think thick carpet padding, maybe certain types of layered floating floors, that compresses too much underweight. The code defines that as more than 1/32 of an inch under standard pressure and is also thicker than 1/8 inch uncompressed. That material cannot extend beneath walls or partitions that are fastened to the floor.
So you can't run the carpet and pad under an interior wall.
Exactly. That carpet or padding under, say, a non-bearing partition is actually destabilizing the vertical support, however slightly. It must be trimmed back flush with the sole plate, so the plate bears directly on the subfloor or slab.
That's a huge potential pitfall. Easy to miss.
Very easy.
Okay, so wood framing is relatively flexible, right? It allows calculated cuts, compensating fixes. But when we move to alternative structural materials like cold-formed steel or SIPs, the rules seem to change fundamentally. Let's look at the limitations and the required discipline for these systems.
That's right. The flexibility you have with wood often disappears. Let's start with cold-formed steel, R603. The code here, specifically R603.1.1, is pretty conservative. It limits this prescriptive use to residential buildings not more than 60 feet long, perpendicular to the span, 40 feet wide parallel to the span, and only 3 stories maximum. And just like wood, inline framing is critical. That's R603.1.2 to maintain that direct load path from joists or rafters down through the studs.
Okay, but what's the big difference in handling them?
Here is the absolute critical distinction. R603.3.4. Wood allows calculated cuts, like we discussed. Cold-formed steel does not. The code says the flanges and lips of steel studs and headers shall not be cut or notched. Full stop.
Wow, not at all.
Not at all. Those bends, the flanges and lips, are critical to the stud's geometry, which gives it its high strength-to-weight ratio. If you need a utility penetration, you must use the pre-punched holes in the web of the stud, or you have to find another path entirely. No field modifications to the flanges.
That's a massive change in field workflow compared to wood. Okay, moving to masonry, R606. What dictates the thickness of a structural masonry wall?
Primarily, it's governed by story count and the type of masonry unit. covered in R606.4.1. Bearing walls that are supporting more than one story above must be a minimum of 8 inches thick. However, for a single-story dwelling, or maybe a detached garage using solid masonry, you could drop down to 6 inches thick, provided the wall is no taller than 9 feet.
And bearing. How much support do beams need on masonry?
Good question. When you're supporting heavier concentrated loads like beams or girders, they must bear not less than 3 inches onto solid masonry. That's R606.6.3. Compare that to lighter loads like joists, which only require 1.5 inches of bearing. It's about spreading that load to prevent crushing the masonry underneath.
Makes sense. And concrete walls are 608, including things like ICFs, insulated concrete forms. We're talking minimum thickness, and I assume protecting the rebar is key.
Absolutely. Concrete walls, covered in R608.3, can range from standard flat walls, which must be a minimum nominal thickness of 4 inches, according to R608.3.1, to various waffle grid or screen grid systems. But yes, the key field inspection point is always reinforcement cover, specified in R608.5.4.1. If your rebar is in concrete that was poured into removable forms and it's not going to be exposed to earth or weather, you generally need 3/4 of an inch minimum cover. But if that concrete is cast directly against the earth, like a foundation wall, you need a substantial 3 inches minimum cover to protect the steel from moisture and corrosion over the long term.
Big difference. Okay, finally, let's look at structural insulated panels, SIPs. That's R610. These are high-performance composite systems, meaning the panel itself, the skins, and the core is the structure. What unique rules apply to framing and utilities here?
Right, SIPs are different. They follow specific standards, like ANSI PRS 610.1. Their plate system, for instance, is unique. That's R610 Palladium 5.1. You still technically have a double top plate, but it's a two-stage process. First, a 2x lumber plate is recessed into the SIP foam core at the top edge. Then, a full-width cap plate, matching the total SIP thickness, is applied over the top of both the recessed plate and the panel skins. It's more complex, ensuring the load transfers evenly into those panel skins.
Interesting. And utilities, can you just cut chases like in wood?
Definitely not. Like steel, utility routing is highly controlled. That's R610.7. You cannot just chop out foam wherever you want. Vertical chases are capped at a maximum side dimension of 2 inches. They must be centered in the panel core, and they have to be spaced a minimum of 24 inches on center from each other.
2 inches max, centered 24 inches apart.
And it gets even more restrictive for horizontal chases. You only get 2 horizontal chases allowed per panel, total. And they have to be placed at very specific heights. One must be at 14 inches, plus or minus 2 inches from the bottom edge of the panel. The second one must be at 48 inches, plus or minus 2 inches from the bottom. That's it.
Wow, very precise.
Extremely. It's all about preserving the panel's structural integrity, which is much more sensitive to internal voids than a traditional stick frame. You're dealing with a stressed skin system.
Okay, let's try to unpack this then. This deep dive really shows that whether we use wood, steel, SIPs, whatever, the code's primary goal is that seamless transfer of load from the roof down to the foundation. Based on the 2024 IRC sections we've hit, what are maybe the 3 or 4 most important, actionable takeaways we need you, the listener, to lock down today?
Okay, 4 key things. First, and maybe easiest to overlook but critical, the floor layer trap, R691.2.1. Get hyper-aware of that sole plate placement relative to flooring. If you are using compressible flooring materials like thick carpet pad, you must ensure it stops short of the walls and partitions. Don't run it underneath, trim it back. It's a simple fix that prevents a potentially major structural compliance failure.
Got it. Number 2.
Second, material dictates penetration rules. Remember R602.6 for wood versus R603.3.4 for steel. This is a non-negotiable difference you have to know. Wood allows calculated notching and boring based on percentages of stud depth designed to preserve the core strength. Cold-formed steel, however, is intolerant. You are absolutely prohibited from cutting or notching the flanges or lips.
Right.
Know the difference before you pull out the hole saw or reciprocating saw.
Crucial distinction. Okay, third.
Third, compensate for every cut in load path members. If you absolutely must compromise a primary load-bearing element like a stud, or especially a tension member like the top plate, whether it's doubling a stud for a large hole in a bearing wall, R602.6, or cutting the top plate for services, R602.6.1, the code provides prescriptive, often heavy-duty fixes using metal ties, specific fasteners, and detailed nailing schedules. Never assume a cut is insignificant. You have to restore the lost capacity.
Right. Don't ignore the fix. And number 4.
And fourth, trust the manufactured system. When you're working with non-conventional materials like SAPs, detailed in R610, you really have to abandon the field flexibility mindset you might have from stick framing. The limits on chase size, location, and quantity are extremely strict for a reason. These are engineered systems. Cutting into them randomly fundamentally alters their design structural capacity. Follow the manufacturer's instructions and the code to the letter.
That is a rock-solid summary, really nails down the key differences and precautions. And maybe for a final thought for you to mull over, connecting back to wood framing in R602. When we talk about load path continuity, think about how that entire structural chain relies utterly on the quality and placement of the smallest connection, the fastener. The code, if you look at table R602.31, for example, differentiates between a 16-bay Hammond nail and a 10-bay box nail for specific applications. It specifies diameters down to the thousandth of an inch. Every time you drive fastener according to schedule, remember that the immense structural stability holding up potentially tons of load over 2 stories is ultimately derived from the precise shear and withdrawal resistance prescribed for that specific connection. The stability of the entire structure literally lives and dies by the fastener. Something to think about next time you pick up the nail gun. And that's our breakdown for today. We hope this gives you a clearer understanding of the topic. For more articles and resources, be sure to visit buildingcodepros.com. Join us next time for another episode. Thanks for listening.